Welcome everybody, AI reading group. Woo! Yeah, okay. This is going to be about neural radiance fields and 3D Gaussian splatting. These are like photorealistic 3D reconstruction from videos and images. Uh, wow, it's not okay. Oh, there we go. Okay. So yeah, we're gonna a little overview. We're gonna talk about previous techniques for 3D scanning stuff. We're gonna talk a little bit about LiDAR, photogrammetry. Then we're gonna NeRF. We're gonna explain that architecture. We're gonna show a bunch of papers from NeRF, and then we're gonna do splatting, and then I'm gonna explain the architecture of that, and then we're gonna also look at some papers from that. But this is more recent, so there's only a couple out. Um, Pause everybody. Video time, video time. We're gonna do it. We're gonna do a demo. If you don't want to be filmed, maybe like, I don't know, walk out of the room real fast. But if you're fine being filmed, then we're all gonna freeze. Everyone's gonna not move, okay? And we're gonna go around the room, okay? So I'm just gonna go and then I'm gonna start. Nobody move. Okay, that looks good, guys. So now I'm gonna
The display's a little moving.
what?
Like you have a.
Oh, so we'll see what happens there then. Let's see.
Oh, it's planned.
It wasn't planned, but
Oh.
okay. Now we're gonna take a little break for me to AnyDesk, and it's to access my computer. It's like remote.
Yeah.
Yeah.
I recommend Rustex, by the way. It's like AnyDesk, but like actually open source. I think.
So now I put it on here to start video. Sorry for those people who won't get splatted. Now I need to, okay, this is a little. There we go. Okay, it's running. We're gonna leave that. We're gonna leave that in the background. So it's using FFmpeg. It's grabbing the frames from the video, and then it's gonna do all the cool stuff we're gonna explain in the background. To be honest, it'll be done in like 10 minutes, but we can let it train for 40 to get better results. So this is the cool stuff. It'll be running in the background while we're doing the presentation. That didn't take that long, actually. I thought it'd be worse. Okay. Great. So let's get on with it. Okay. That was good. I made that, by the way. I spent time anyways. So what do we want, guys? Question for everybody here. What do we want? Is it money? Is it power? Is it fame? No, we want photorealistic virtual 3D objects. That's what we want here, okay? Better yet, photorealistic virtual 3D objects of things from the real world, okay? That's even better. You look at it and you can't tell that it's fake and from virtual. Yeah. So you can't tell. It looks real. It looks like from something taken from the real world, like a picture taken of something from the real world. Yeah. So let's start simple. So how do we capture 2D information from the real world? I didn't animate this, so I kind of just told you. You take a picture. So from any perspective, you can take a picture with like RGB and you get 2D information from a single point.
Oh, there we go.
Okay. Yeah. So yeah, side quest. Is this AI generated? Do you guys think it is? Yeah or nay?
Yes. Yeah.
I found on Google the first one. I don't think it is. So yeah, that's
camera on the back.
What?
What is no camera on the back?
I personally generated that image.
Oh, really?
Yeah.
You put it on top of person taking.
Yeah.
Oh, okay.
Yeah.
Then maybe not.
Wait, how many fingers they have?
Yeah.
They have a bag of our fingers. Okay.
That's not holding your phone.
No, I mean like you know, not that. Yeah, that is weird. What the fuck?
It's the classic I claw my phone.
Those fingers might be merged together also.
Oh yeah.
I'm not sure if that's.
You guys are hallucinating. Like again.
Oh god, just like LS for real.
Really. Maybe not. I don't know. First Google search though. So unless we've already been infected by AI. Anywho. Okay. So how might we capture 3D data, right? What's the third dimension? Again, I didn't animate this. I should have. What's the third dimension, guys? It's depth. No, who said time? That's the fourth dimension.
No,
we have to have.
That's a real video generation person.
Yeah. But we have depth information. So besides just taking a photo, we want to know how far away each pixel in our photo is away from the camera, right? So one way we can do this is called LiDAR. LiDAR, wait, what is this? Okay, yeah, ignore this. But LiDAR pretty much works by sending out a laser and then measuring the time it takes for it to come back, right? And then this is actually a cooler diagram. It like sends a laser and then it like sends it down to a receiver and it can start the timer and then it figures out how long that takes. And then you get the distance because you divide, you use that time of flight times speed of light divided by 2, and then you can figure it out. So it's kind of cool stuff. So here's, if you want to then get like a picture of LiDAR depth information, you actually kind of need a grid of these LiDAR lasers, right? So here's a little quick video.
Spins so that the laser scans horizontally, while the swing mirror deflects the laser beams vertically. As the beams constantly change direction, a single laser could achieve a similar scanning pattern as a mechanical LiDAR with multiple lasers. However, it takes an incredibly high speed frame with just one laser beam. While a mechanical LiDAR spins 10 rounds per second, the scanning mirror of a single laser LiDAR has to spin hundreds or thousands of times. This shortens the lifetime of the mechanical parts. Another solution is to find integrated scanning solutions, such as MEMS modules, the core of which is a micrometer level scanning mirror. Driven by thin cantilever beams, the mirror periodically rotates around the horizontal and vertical axis at high speed, reflecting the laser beams to change direction. However, the MEMS approach does not meet the LiDAR industry's ranging.
I think
Will that cause like really bad rolling shutter?
yeah, things are moving a little bit, but yeah, there you go. That's how it does it. You can do you can send out a bunch of lasers, you can get really small ones, you can do a scan line of lasers, right? But again, the whole point is you're trying to construct, you're trying to get depth information along with your images. Okay, so how does this help us with that photorealistic, like objects and whatever?
Polygon mirrors.
Okay, how do I? Oh, there we go. So like from one perspective, we can take like a picture, and the picture now isn't just a picture of color. It's a 3D picture. So you can kind of see it's kind of cool here. It like only hits him from this side because again, you're only from this one perspective, right? But then again, we want 3D objects. We don't want 3D pictures. So how do we do that? Well, what we do is we can take multiple 3D pictures, right? Like let's say from the left side of someone on the right side, and then we learn how to actually merge them together. So if you like, this is a cool scene of somewhere, but they took a LiDAR scan from one side. They probably had a long range LiDAR scanner and another. And then they do something called point cloud registration, where you kind of just try to move them as least as possible so they match up to have the most overlap, kind of. So then you can merge those 2 point clouds together and you kind of get like now a 3D model because you're taking a bunch of 3D pictures and merging them together. Yeah, again, another one. You can kind of see it's like literally like a photo. You can't see there, but then from this one you can see it and then you can merge it into a single point cloud. Yeah, so each of these, by the way, yeah, this is called a point cloud. When you have these LiDAR dots that get sent out and they hit something, you get the distance, and then those are pretty much points, and then the next laser or LiDAR dot is your next point, and then you get a bunch of them, you get point clouds. You can think of these as point cloud snapshots, and then you can merge them all together to create a single point cloud of your scene. So now you have a 3D representation of it.
What's the difference between point cloud 1 and point cloud 2 and then merge them?
They're taken from different angles. So like imagine I took a picture from here, right? And then I went over here, right? I can't see like the left, like for example, the face. If I can see the left side of your face and I get the right side. And then now I can put them together. Now I have a model of your face.
And you can turn around and see every face.
You can see every side. Yeah, now I can see a bunch of different angles from it, right? And again, it's because it has that 3D depth information. Now it's not just an image. You can see that and then it can match it and then they merge together, right? I think they use other techniques and stuff, but point cloud registration is kind of the general gist of it. Yeah, quick aside though, like let's say I have a scanner, I'm going like this. I don't want to treat these all as just independent frames. I actually know that this one moved like this much away to get over here, right? So we can use like the IMUs inside scanners to figure out, okay, I moved from here over here. So you should probably, the initial guess should be that this thing should be rotated or moved this way, right? So it's easier than just saying, okay, this guy, figure out how to move them. It's like, no, I'm probably gonna need to do this translation. So for example, we have this image of just a stationary car, right? And it's doing a LiDAR point cloud. And look, it gets the accurate distance to all the objects, right? Or the scene. But let's say the car is moving, right? You're actually LiDAR scan once you do a full construction, because again, it's a sweep line. You're gonna be off, right? So you need to account for this motion. And again, if you have a scanner, you're going to put that like an IMU or something that measures acceleration to actually get an accurate prediction. Because you can see like here we didn't move that much when we scan here, but here we moved a lot, so we need to adjust for that. So little side. Woo! We have our point cloud.
Yeah.
Okay, woo! Yeah. Yeah. Okay, what do we do with it?
Looks cool.
What can we do with it? I found the most like the least resolution gift I could find. We can create 3D meshes. How we do that is pretty much for the point clouds. We can literally just form faces by treating these each point in the point cloud as a vertex, and then we can form them together. And then like I think this is the same image, and then we can make cool ones, or you can like construct things of yourself. And that's my nose. Yeah, cool. We can make 3D objects. So, oh, am I gonna do this? Yeah.
For the LiDAR, like do you adjust the heights or only like the XY axis?
What do you mean?
Like for the LiDAR, when you scan, do you adjust the heights as well, or only like moving?
Yeah. So, I mean, back to this video. There's multiple ways.
Polygon mirror spins so that the laser scans horizontally on laser beam, while a mechanical LiDAR spins 10 rounds per second. The scanning mirror of a single laser LiDAR has to spin hundreds or thousands of times.
So it depends what your system is, yeah. And it might be rolling like kind of shutter, as Jordan says, in certain directions. Because if you sweep here and then it moves, it's gonna like look slanted. Yeah. But yeah, so here we have our, I don't know if this is gonna be too long. It's fine. I have a LiDAR. It's okay. Okay, ones you don't have a LiDAR scanner though. Shoot. I used this gift in the last reading group. LiDAR scanners cost a lot of money, especially like really good distance ones as well. And even like I want to do the demo. How much time do I do that? I could do the demo. Real quick.
We can do that.
I can do a demo.
Yeah.
Okay, I'll do a demo. I'll do a demo.
Just spend money on flower scanner.
No, I have a camera.
Oh.
And I'll show you something really cool. Wait, shoot, do I have let me see.
LiDAR projection. It's just countless depth estimation.
Crazy LiDAR, guys. Crazy LiDAR. It's gonna be crazy. This works. Okay, this is something. Wait, can we turn off the lights?
Yeah, sure.
Wait, how do I change my screen share? New share, desktop. Okay, let's see if
What are you doing?
something.
What are you doing?
Allow.
Let's like just hate this.
Oh, there we go.
Oh,
so so what I did is this is an infrared camera right here. And I blocked the light sensor, so it thinks it's nighttime right now. And what it's doing is, see these LEDs right here? It's having it so these LEDs are producing infrared light. So that's why they're red. They just want to indicate to you that, hey, like shining like infrared light in your eyes, you can't see. Oh no. Oh. Let's plug it back in.
Oh.
No, it's wait, let's see. Photo booth. Come on. Okay, there we go. Okay. I'm gonna be very delicate with it. But yeah, so this is what it's doing. If I cover this though, you can see this is just my I'm gonna move these, I'm gonna bend these out of the way. Look, so this is just, it's looking at me with LiDAR, right? Now watch this. I'm gonna go to my phone and I'm gonna open it. Whoa, what just happened there? Do you guys see that?
Oh.
What just happened there? Huh, my phone just unlocked. Let's go to the front camera. Whoa, what is happening? Do you see this? This is actually 10,000 dots. This is just rolling shutter that's happening, but you can see these are actually dots that are my front camera's projecting onto my face. And it's using this for depth estimation. If you look at a front camera, if I go to the wall or something, you actually see it does a coarser grid of LiDAR points, right? So this is for longer distance. These are stronger LiDAR that this is like a Pro, so it has the front-facing LiDAR, right? And like it can go, oh wow, it can go, where's Jordan? There he is. Is it, oh, it's kind of, you can see it on the table. Yeah, there. See the dots? Yeah, there we go. But the front-facing LiDAR is not going to reach that far. It's only going to reach here, right? But they have a finer, coarser grid of them because they want finer depth estimation. So the point cloud is really rich here. And then you scan your face, you go like this, it creates a bunch of snapshots. Then it creates a 3D model probably of your face and uses that to unlock, right? And then again, this LiDAR right here is more distance. I think it's like 10 to 20 feet or something. But yeah, they use LiDAR in your phones.
That's great.
There you go. Very cool. Very cool. That's all I want to show. Lights back on. Yeah, I'm pretty sure the front is an actual LiDAR. The front facing the normal camera is an actual LiDAR, but the front facing camera, I'm pretty sure, is just like a LiDAR camera. Like it's not measuring time. It looks at the warping and distortion because the grid is uniform. And if the grid is more fine, that means that part of the grid is closer. So it's not actually doing time to a flight for the front facing LiDAR, Face ID. But then for the other one, I think it is doing time of flight. That's my guess. Anywho, let's say you don't have that though. Even this, like the front camera isn't going to be good enough to get like image quality kind of scans, right? It helps in it. It helps in autofocus and things like that. That's why they have it, but it's not great there. So what we're going to do is something called structure from motion. You can just use your normal camera. I was tricking this whole time. LiDAR, completely useless. You didn't need that. To be honest, nobody really cares to do this for 3D scanning at all. You can use your phone. It's called structure from motion. Okay, how does this work? So structure from motion is kind of cool. Instead of, let's say, remember when we had the point cloud snapshots, right? To merge them together, it match similar features. Like there's a column here, a column here. It's like, okay, those probably go together, right? But what happens if we could just do that with images? So instead of getting depth information from LiDAR that is active when we bounce off something, what we're going to do is we're going to get depth by looking, by comparing features between frames as we move our camera. And then using like linear algebra and math, we can see that, hey, if these points got farther apart, then maybe we moved an angle. Or let's say these points got closer together, then we probably moved back, right? And if we track enough features, we can do the linear algebra to figure out how we're moving in space. Yeah, that's how this works. Yeah, and then you can do color. You know what? I'm gonna do another live demo real fast. Another live demo. This is like a live demo day. We're gonna show cool stuff. Again, like once we get to the AI stuff, it's kind of just neural network everything. But so what we're gonna do is we're gonna go to rendering. Wait, what is it? We're gonna go to VFX. We're gonna go to motion tracking. Okay, and we're gonna drag in our video, guys. So this is our video, guys. I think HDR was on. That's why it's so whited out. But anyways, what we're gonna do is we're gonna bring this up, right? And what we're gonna do is we're gonna click detect features. And whoa, what did it do here? It detected features. It found places that it thinks, for example, we can look at this one. We can click this one. That would look good and track between frames. So then we can actually click this forward button, and boom. Whoa, what is it doing? It's track. So again, oh, we should pause. Okay, it's not letting me pause. Whatever. It lost some of them because some of them don't exist anymore. But if you actually look here, we can click this, I think. Metadata. Let me see a track. Oh, track. There we go. Look, that's the feature I'm clicking right there. So I can click this feature as well. But let's click this feature on the laptop. And you can see it actually tracks it. See, look at the top right? That's what it's consistent with. And that's that feature right there. And it realizes, that's the motion of that one. And that one's falling similar. And that one's falling similar. Then the motion in 3D space should be this, right? And that also means that we know where all the rest of the points are relative to that, right? So we can figure out the tracking of a 3D camera in space. And we can also figure out the geometry of the objects by inferring it from how the camera is moving around them. So, but yeah, look at that. Whoa, look at all the little features it tracks, and they can see it in motion. And then you go here, you lose them. But then what you do is you just click detect features again, and then you track those through time till it loses them. And then now we have these new features that we tracked, and we keep going. And then you can actually just go to a point where you just click solve from camera motion. It's not going to work because you have to clean up a lot of data. But you click solve from camera motion, and it just solves your camera motion through space, right? And this gets us the depth information, merging all this stuff. And what we can actually use is these can be like seeds for our point cloud, because we know these are very consistent and we can do other points around that. So this is the basic idea behind structure from motion and photogrammetry. And you don't need LiDAR for depth estimation anymore. You just have multiple frames captured from different angles and have trackable features between them. So yeah, another live demo. Oh, this is great. This is so cool. Okay. Yeah, question?
Like,
yeah.
How do you fix it? Make sure that
What do you mean?
those little squares.
Yeah.
How do you fix it? And then determine the path.
How does Blender actually does
So I think it's like some ML, like if it doesn't, it does like a bunch of like little candidates of edges, and then if it sees they're consistent between frames, because look at the top right. So we're gonna scroll through some frames real fast. So look at it. It looks pretty much the same, right? You see how the general image of the feature is generally the same. If it isn't the same, then it's not a feature you could track, right? But it's generally in the same area and it only moves slightly over. Maybe they use some like flow estimation. I don't know. But it has to be like things that like I think it's a neuron or it's some kind of filter that looks for like if it doesn't change 80%, it's probably the same feature. I don't, it might be. I don't know. I don't know how Blender implements it. Yeah. Might be an algorithm. Wait, question, Leon? Here you go. Yeah. It's kind of cool. Whoa. Okay. Anyways, back to this. So then we have our things. We know how it's moving in space. So then we can figure out how the like geometry of it is. But then we want color. So what we can actually do is get those images while we were doing it. Again, we had LiDAR. We got like the 3D objects, if we want to go back to that real fast, right? We got these, right? And we can get those. So we want that to have color information. So what we can do is we realize we took this LiDAR scan from this single perspective. And if we take an actual image, we can project that color onto it from all the angles they were taken from. And the same thing with this, we do our photogrammetry, right? And we figure out the motion, so we can figure out the geometry of it. But then once we figure out geometry, we want to project the color. So we actually can project color information onto it using just like projection math of like, this is the geometry of the scene, this is the image, put that color, like wrap it around that object. And that's what we do here. So this is good. This is like insanely high quality, by the way. I can show you the original video. It's pretty, actually, I'll show you the original video. It wasn't that crazy. Where am I going? 3D scans, our teen head photos. Teen head, oh, here it is. This is the video. This is not like that insane, you know what I mean, to get that detailed of a scan, How long? Yeah. I mean, and we can actually look at the model like that. That was it. So there we go. Right. That little frames. And then I break that into a bunch of photos. Right. And then I feed that into a photogrammetry thing. And test raw. Here we go. So look how good this is. I don't know what the file is format, but look at this. Like, look at this. Look how high quality that is. That's like a little too high quality. Yeah, a little too close, a little too personal. But yeah, look at that. It's pretty good. It's not that bad. But again, that was a lot of passes and it was very close. And again, this is like pretty good, but I'm not sure if you can call it photoreal from every perspective. And you need a high quality amount. So it's okay. But there are also, I just wanted to show, I have a 3D printed that. That's my head. Look at that. Look at that. Wow.
That's
okay.
crazy.
Anyways, but there are kind of problems with this though, because again, the coloring and stuff. It gets worse, again, angles and if the geometry doesn't get right and you don't have enough passes. So I did this with less images, not that great. And then the ugly, yeah, I get that and ugly. Okay. But the problem is when we're projecting, if we're projecting texture and we don't get nice projection math stuff, that's my hand. But then it thinks my hand is on my body here. Because again, it had to use the color information from this one angle and it thought it was more accurate. So this is a problem. Also, let's say like you're in the sun, right? And from one angle, it's really sunny. You're going to look super white. And then you look from another angle in the 3D model, it is projection. It's still going to be white, right? So that idea of specular from different angles, you have different colors. That's another thing this doesn't account for. Yeah, and you also have these kind of texture schemes. I found this paper, it kind of worked on this stuff in coloring. But the main thing that is like this color stuff is baked in and angles and a lot of little issues. But it's a pretty good technique for photogrammetry and scanning stuff. You want to have fun with it. Photogrammetry live demo. No, I'm not going to do that. Yeah, so there's 3D scanning apps. Most of these are paid for, but this is pretty much what they do. They do photogrammetry. And if you have like a LiDAR front facing, they use that a little bit to aid in it. Then they just do that structure from motion. They do the geometry mapping. They do the texture mapping, and then you can get a 3D scan. Yeah, this is like available out there. Yeah, question.
So the 3D picture that they're bad.
Yeah.
Yeah, what cost like the results?
I think it's a low number of photos, maybe. It's weird that it got the geometry of my body. We can do our teen body. Where is yeah, I think it's just a low number of photos, right? And tracking might have been bad. There might not have been enough tracks, so then it thinks one part is somewhere else. Yeah, I mean, like, look at the geometry of some of these. Like, again, the seam stuff you can kind of see, because it didn't track enough features. And if it can't track enough features, it has to just do a linear interpolation, and then it looks like a flat thing. But if you have a bunch of features you can track all along this, it can do a curve, right? Approximation. But that's the problem, is that because it's trying to do a 3D geometry from a point cloud, it's going to have a problem if the point cloud isn't rich, right? But we want it, so even if the point cloud's bad, if we have a good looking photo, it should look photorealistic from the same angle. Like, again, like this angle I probably took in the original picture, but why does it look so bad? It's because it's trying to optimize all the rest of them. But what we'll see with neural networks is that what it'll try to do is optimize every single input image you gave. So if you're looking from the original perspective, it should be photoreal, right? And that's hopefully means if you vary slightly, it's also going to look photoreal. But that doesn't guarantee if I go like up here. If I go up here, it looks pretty bad here. But in the AI model, it might look even worse because it has zero data from that angle. And it tried to over-optimize for the other ones. We're kind of like overfitting to our input images when we go with AI. But yeah, this is funny. I like how the hand literally projects onto the, that's a cool, yeah. Anywho, slides. Okay. What's the time looking like? Oh, this is good. Yeah. But I want photorealistic. We want photorealistic. We are here. We are here now, guys.
We're so back.
We are so back. Neural radiance fields. What? Okay. I looked this up. I don't know what the motivation, like growing need for immersive, realistic digital experiences. Sure, I guess. I mean, I don't really know what the motivation too much was, but it was like, it's a cool thing. So again, I was gonna make slides and stuff, but I realized every NeRF and Gaussian Splatting like website, they have a blog. Every paper they have a blog, and look how like amazing this is. Like look how nice this is. And they have a video where they go and they explain their paper to you. And like I'm not gonna compete with this and try to make it. So we're just gonna like watch a bit of the videos because these are like really good.
Results of view synthesis. Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation of the scene as a vector-valued function, which is defined for any continuous 5D coordinate consisting of a location and view direction. We parameterize this scene representation as a fully connected deep network that takes each single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We can then use techniques from volume rendering to composite these values along a camera array to render any pixel. This rendering is fully differentiable, so we're able to optimize the scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images.
Yeah. Makes sense? Super easy, you guys got it? Okay, no, we're gonna go over it. Okay, so the first thing they do is they have to figure out, they get a bunch of pictures of the scene, right? But they need to know where these cameras are in space. And again, we use structure for motion. They actually say it. They use this library called CoMap. This is what like all of them use because they first need to figure out, okay, yeah, where the cameras actually are in the scene. Because again, you're inputting XYZ coordinates. So you need to know where the camera's pictures are taken from. Yeah. So yeah, this is still relevant though. This photogrammetry, structural motion, you need this to do camera, but maybe not the point cloud. So here's NeRF. Here's the actual thing. Again, I'll go back to the video if we need more explanation. But the neural network tries to take in any point in space, right? And the direction you're looking at it, so theta and phi, right? And what it wants to do is predict for that point in space, what color should that be and what transparency should it have, right? That's the network. That's the network part, right? How we actually query that network, though, is that if I have, like, let's say I want to go, I would say, what network? What does it look like from this perspective here? I do for every pixel, I shoot out a ray, and then I sample along that ray, asking, hey, network, at this point, and I'm looking at this angle, what is the RGB alpha? And it's like, oh, it's like kind of like, you know, it's really transparent. There's nothing here, right? And I'm like, okay. And then I move along the ray and I sample again. What's here? It's transparent. But then let's say when I hit the ground or something, it's going to say, okay, that's like black, and it's like transparency is like, it has no transparency. And then once my alpha is filled, like I have a full transparency, that means the ray stops. And then I sum all the colors weighted by their alpha, and that's the color for this pixel, right? And I do that again. So this is pretty much ray tracing, right? But again, we're sampling along the ray, and each of these samples is querying a neural network to give us an RGB value. This is like extremely slow if you can't tell. For a single pixel, we have to query the network however many times, and then we have to do that for every pixel.
How big are these networks usually?
I don't know, actually. I don't know. We can.
Like, are they like normal in this classifier levels, or are they like the diffusion model levels? Or like,
let's look.
What's the classic ECC formatting?
Yeah, I don't know what this is. Data set. Did they say model? Related work? No. Let's see. Oh wait. Oh. Here.
Oh.
8 fully connected layers.
Relative
Relatively 6. That's it. Wow.
Oh, that's actually not bad.
Yeah, it's very lightweight. Pretty
Yeah.
lightweight. Yeah. So yeah, that's what it does. That's the network. How does it train though? Right? The training process is
results reducing this.
The training process is we have ground truth references of I took a picture from this point in space and this looked like. And I know the camera was then here, again from structural motion, then here, right? And we have all these different photos, right? So to optimize this network, where I should be able to query any point in space, say, look at it from this angle, what is it? What color? What color? What color? How does the network learn what this space is? Well, what it does is it looks from one perspective, shoots out a ray, queries the network, renders it, and gets that pixel color. And at first, it's going to be randomly initialized. That pixel color will be wrong. But what it's going to have to do is learn that when I query your network, again, let's say these colors aren't correct. When I query this network,
results for view synthesis, location, and view scene representation.
When I query this network, when I sum all of them back up, that color that should be produced is yellow at that one spot because there's a bulldozer, right? And what that learns to do, again, it could just be that the bulldozer is here, it's right in my face, or it's one that's really far away. From one perspective, I can't tell. But if I have another perspective, the only way for the model to be consistent is that the bulldozer isn't just 2 images in front of our faces. It's a 3D thing that exists here that we're both looking at, right? And that's this idea right here, right? Is that all the camera perspectives contribute to that. And for the neural network to actually, to train the neural network to learn that this 3D space actually has this color when you look at it from this angle, you have enough photos that when you do that ray tracing rendering and you're querying it, when you query it, it should be rendering what the actual photo was from that perspective. And if you have enough of them, that means that when you go for an unseen view that you've never seen before, it should be good because the neural network learned how to color any point in space. So again, back to this is a very simplified diagram of that, right? The neural network has the information. No, it doesn't. There's no information. Just the photos. Yeah.
Well, it's trained on just the photos.
It's trained on just the photos. So you input.
Do you know for like small type like that how many cameras is needed? Like for
it's a wild train.
I think they did low as like. I think there's some good ones like 40 images. It depends how many you need from each angle. Again, there's a problem though, like just two, it can do that trick to you. Like it can put an image in front of your face and then like over here, an image in front of your face of just the angles.
Yeah.
And then like you go to any other thing, you just see two pictures standing there, there's no object here, right? And you're like, wait, what happened? Why'd you do that? So it can kind of trick you. But yeah, that's the basic idea. And again, it's trained so that how that network is trained is because we're trying to make it so that when I create this network and I do all this process, it should be getting the actual images. And then I can backprop the difference of, hey, every single pixel, and I know every pixel difference. And then I can have that make it so the sampled things along the ray are like more yellow, let's say, if it wasn't, right? So I can push the color directions of the MLP to predict yellow in the direction of the things that should be in that space, if that makes sense. I think
So
yeah.
I want to understand the training task. So is it training to predict like all the pictures or?
Yeah, it's pretty, so what it's doing is you give it the original, like an actual photo camera position in space that you took in the original. Then you have what the actual image was. What you do is you ask the network, hey, render an image for me right here. And what it does is it does a sampling on the array, sums them all up, does sampling on the array, sums it all. This is a horrible image. But we do is we backprop by getting the actual image and saying, compute the difference. MSE, yeah, we do the difference of the image.
So you give the position and try to predict like the RGB of the pixel of that position.
Yes.
So what's the input?
So the input is coordinates in space and the angle we're looking at them. So for example, this one pixel, let's just consider one pixel, right? Let's say we want this looks like it's supposed to be flat, let's say. But let's say this is like all random colors, right? This pixel right here is black because what we did is we shot this ray out from this pixel. We know where this camera is in 3D space, right? Then we created the network for this XY position, then this XY position at this angle. And we kept doing that. So we know that the sum of this pixel is going to be a bunch of network queries, right? So you can think of so far our function so far is the sum of a bunch of network queries to all the networks. And then we sum them all together and weight them. And then we compute that sum of all of these network queries right here. And we do the difference of that with the actual predictive, the color of the pixel should be. And then we can backprop through all of these at once, right?
So the network doesn't have any information about the original object, like what does it look like or something?
No. Well, I mean, all it has is this is what it should look like from this angle in this camera position in space. Yeah. It has no other 3D information. Yes, Maxine?
XYZ is like some projected 3D space. Is that what XYZ?
Yeah, it has to because I mean, what is this point? What is this point? Is it yeah? So what it does is it puts in a uniform boundary of 0 to 1. It tries making it so this entire scene is represented in 0-1 boundary. We'll actually show that papers that fix some stuff because if you go, this is good for objects, but if you go to unbounded scene generation, like really large scenes, it really messes up because MLP has to stretch really far to do boundary stuff. So there's ways to do some kind of common filter and mapping, like space stuff.
Does it go from image to like the XYZ with the classical stuff, like combining the camera?
Yeah, classical rendering techniques, right? It's
like scale colors.
Yeah, it's again, it might be nice to think, oh, pass in the XY coordinate of the image and angle, and then ask for an image at that position. That's not what the network is doing. We're using classical techniques of saying from this camera position, query the network. The network is predicting for a point in space what color it is. And then how we're actually doing the rendering of the images is classical ray tracing techniques by doing querying of the network for what the color that position is in 3D space.
This kind of reminds me of like back in like 2015-ish, they used to try to do a thing where like they were like, oh, if I inputted the XY coordinates and the frame number, I want to compress an entire video into a neural network. They used to do stuff like that, and it feels just like this.
So what's kind of cool is, yeah, a lot of people compare this to like compressing 3D like scenes. Like maybe it's cheaper and higher fidelity than
actually storing
like the geometry files that might, yeah. So like, or just store the picture. Like it's neural networks you can think of just like compression, I guess. Like GPT is just compressing like how many terabytes of text if you want to think about it that way. So yeah. So here's some tricks though. So we're sampling so the ray stops once we've sampled enough where the alphas are they all out like the the transparency, like it all adds up to 1, right? That means we can't see anymore. Like if we looked, like that's a glass door right there, but it hits the floor. I can't go through the floor and see more than the floor, right? But what we do is we don't, again, this is a dense stepping coarse estimation, and that's not that good. So like they do in the paper, it's the first trick they do. Where there's higher density, let's say this point's like, it's a lot of alpha here, we sample more, right? Because again, if there's a lot of alpha here, then it might have been alpha a little bit before that we should take this color more, and we need to figure out, oh, like it just happened the back part of this was yellow, but the most of it was black, but like because our dense sampling, we happen to grab there. So it's like, if it's a high density value, we care to break that part up and then sample finer, right? So instead of this dense estimation we do at first to do the sampling of the network, we then do it again here. And that's the first technique they do. The second trick they do, this is actually very, very important. I like think about this a lot, is the fact that you can't actually just pass in like XYZ coordinates to networks. Networks in general have a tendency to learn very low frequency features. Probably because like, if you think about it, like maybe it like optimizes the loss of like this whole room. Like if I have to do something very basic, I just make it like mostly white, and that would be mostly correct, right? That's the lowest frequency feature. But what they did is for every XYZ coordinate they passed into the network, they actually created Fourier features for every single one. And this is exactly positional encoding, I think. Yeah, this is pretty, like, it is positional encoding from transformers. But however, in contrast, they use it not to, they don't use it to actually encode like a sequential position, but just spatial position, right? But it's the exact same thing, where instead of just passing an XYZ coordinate, we first convert an X coordinate to a Fourier feature of increasing frequencies, same with Y, same with Z. And this actually lets the network learn. So yeah, we're gonna look at, real fast, we can look at that, I guess. Yeah, if you just look at these images, right? This is just passing XY to it. So again, this is in 3D, this is 2D. But you can see how, in general, it goes very blurry, right? But if we pass in first through 48 features of the XY, we get very good results. Actually, I want to go to the thing. Any questions about that, though? Sorry, I didn't ask. Any questions about the first trick? No, I think it's pretty self-explanatory. And second trick, I'll show the video right now. It's also just in the follow-up. If you go to NeRF, so look how amazing these are. By the way, every single, I don't know why, is it like standardized? But like every NeRF paper, there's like 200 of them. They all have a blog and like a video. Like look how good this video is. Like seriously. So we're gonna go to follow-up works though. This is it. And we're gonna look at this. So yeah, this is just passing in XY coordinates. It's just learning how to encode an image, not a 3D scene representation, all this training regimen, whatever. And you can see that's what it does. But this, they pass in Fourier features, and it, like, look how fast it went. What? No mapping, XY. So they pass an XY coordinate. They say predict the color at this image, the XY, right? So they're learning to encode an image, and then.
Sure, it like converts every X into like several features.
Yeah, exactly. Yeah, it. Like in a positional embedding, exactly like a positional embedding. It does. Oh, wait, not on the slides anymore. But yeah, it does it with this. So take an coordinate, put it through a sine wave, put it through a like phase, and then higher frequency, and then now you have a vector that you pass in pretty much like a list of numbers, and those numbers the network can better work with. Yeah, but you can see this one, like it trains. I can't even show how fast the first one train. Here, let's see if we can. I tried to like look at this, right? Boom, boom, boom. Right, that's crazy. Because again, it's letting it look at the high frequency features. Because in general, for MSA loss and that kind of stuff, looking at the features, it's like, well, most of these are, you know, in this color range. But if we pass in these richer things, explore like kernel stuff. But yeah, it's important that if you're gonna pass, this does not work at all. Like NeRF does, yeah. Well.
I'm just curious, in the graph, they say Gaussian Fourier features. Are those like different from the Fourier features, or I'm just a little bit
Gaussian, wait, and here it says this is Gaussian. Let's see. No, I don't think so. It's just a normal Oh, yeah. I think they don't do uniformly. They actually do a Gaussian sampling of frequencies. So they don't go two times this frequency, two times this. They do a random, they pick a bunch of random frequencies, and I think it works better somehow. I don't know. I think, yeah, I think that's what they do though. Yeah. Any other questions? No. Okay. Okay. That's the trick too. Yeah, and I put that here just to have. Okay. You guys get NeRF now, right? Super easy. Okay. Yeah, great.
That one was 2D, right?
What?
Like 2D images.
The images were 2D, but the same applies to 3D in that if NeRF
XY to XYZ.
what do you mean?
The difference between 2D text and 3D text for NeRF is the input. Now you're covering XYZ.
Yeah. Well, also it's also X, Y, Z and theta phi, because it's not just position, it's angle. So they append that information onto it. Yes.
Yeah.
But I mean, I think they tried it and like it probably looked so bad if they just passed in XY. Like we saw what it did for 2D. Imagine 3D. That'd be way worse and probably take way longer. And they probably couldn't even train to this level.
Like the one doesn't have any information about the image. Probably just guessing at the beginning, right?
Yeah, I know it's randomly initialized. It's pretty bad, but while it's training, it's probably hard for it to learn these like high frequency features, right? So then, even in NeRF, it'd be 3D. It'd just be those like globs probably that are very smooth, and not like these defined edges and stuff, which are higher frequency.
You know how long it would take to train like that?
I don't know. I mean, look at this graph, right? So they can stop right here, and that's probably good enough. But to get, I mean, yeah, it's never going to reach the same amount, right? So it's always going to be way worse performance. Yeah. Maybe it gets there, but I mean, that's a lot. So yeah, they let them learn it. It actually just doesn't work without doing this Fourier embedding of positional stuff. Okay. Now we're actually going to look at some case studies. These are papers that came out. So NeRF came out in 2020 by Berkeley. By the way, like every NeRF paper is Berkeley. But we're going to look at some cool ones up till now. Yeah. So to be honest, yeah. Okay, MIP again. These blogs are so good. Like, I don't know if I should speak. Like, I feel like we should just. I think this whole thing is like amazing, actually, isn't it? No, this one's so good. Yeah. Okay. I think we're just gonna watch a YouTube video real fast. This is like really.
Hi,
good.
I'm John Barron, and in this video, I'll be presenting MIP-NeRF, a multi-scale representation for anti-aliasing neural radiance fields. First, let's review NeRF. NeRF stands for neural radiance fields, and it's a very simple and powerful way to use neural networks to do novel view synthesis. The basic idea is that you trace rays through each input image, you sample points along those rays, you feed those sampled coordinates to a neural network that predicts a color and a density for each sample, and then you do alpha compositing along the ray to render a pixel. Just doing this a few billion times while minimizing a loss against the input images will give you a network whose weights encode the shape and color of the scene, and that lets you render new views from angles you didn't see during training.
Yeah, we know this.
The goal of this work is to address a fundamental flaw that NeRF has in terms of aliasing and how it deals with scale. Let's see what that problem is. Here's a short test set sequence from one of the scenes in the Blender dataset that NeRF used. And here's what a rendering from NeRF looks like at a full resolution. It does a great job, and so the SSIM score shown here is close to 1, as we'd expect. But here's what happens if you render that NeRF from further away or at a different resolution. Instead of a nice photorealistic reproduction of the ground truth, you start to get a lot of these jaggies, and the SSIM drops a lot. You can try to train NeRF on multi-resolution data, but that doesn't fix this problem. Performance improves a little at low resolution, but gets worse at the high resolution, which isn't ideal. And here's our model, which we're calling MIP-NeRF, trained on the same data, and you can see that it's able to produce high-resolution renderings across multiple scales, instead of just at a single scale like we saw in NeRF. Additionally, MIP-NeRF's performance doesn't degrade when it's trained on multi-scale data, unlike NeRF. To understand why this is happening, it's helpful to review some image processing basics. Let's say you've got an image like this one here, and you want to downsample it. One way to do this is just basic resampling, where we just grab 16 rows and 16 columns from the image. This is a really bad way to do downsampling because you get these awful aliasing artifacts, which people in the graphics community usually call jaggies. The fix for this is to filter your image before you sample. Here, I'm just applying a Gaussian blur and then doing the same sampling I did before. And you can see that because the image was properly filtered before sampling, you get a reasonable looking downsampled result. But if you want to generate a lot of different resampled images at different sizes, this procedure can be very expensive. That's because for each new image size you want to generate, you need to blur the image again, and this really adds up. People in the graphics community saw this problem and came up with a very effective pre-filtering strategy for this, where you just pre-compute different copies of the image at different scales. This sort of representation is usually called a MIP map or an image pyramid. Now, if you've pre-computed a pre-filtered representation of the image like this, then you can just do a trilinear interpolation into the MIP map at the right location and the right scale to quickly get a properly downsampled image. This trick is ubiquitous and is used all the time in real-time graphics engines for things like texture mapping, where you need to be able to resample quickly.
So this is like
in the original NeRF paper, most of the main,
like if you're rendering from far away and then you move away, use the lesser one as well.
Just like
Interpolate between them. Yeah, that's like that's
results were on these scenes of objects floating in space with a hemisphere of cameras around each object pointing inward, which you can see visualized as camera frustums here. Part of why NeRF performs well on this task is that all of the cameras are placed at the same distance from the object. What this means is that NeRF can do view synthesis without ever having to reason about scale or aliasing. But if you start to add in new cameras that are pulled away from the object, NeRF starts to break down because it's a single scale model trying to solve a multi-scale problem, as we saw on the Lego truck results earlier. Our goal with MIP NeRF was to fix NeRF such that it doesn't produce aliased renderings, the same way that MIP maps fix imagery sampling, hence the name. Of course, actual MIP mapping doesn't work for this problem because images and neural networks are very different things. So to fix this aliasing issue, we had to dig into the details of how NeRF works. Now let's look at exactly why NeRF is aliased. NeRF works by casting a ray through each pixel in an image and then point sampling coordinates along each of those rays.
We know this.
NeRF renders a whole image by just rendering each single pixel individually, so we can just think about how one pixel is rendered. In NeRF, each coordinate along each ray has to be transformed with what's called a positional encoding before being passed to the network, and we're going to denote that positional encoding function with this gamma function here. So that was NeRF, and this is MIP NeRF. The first big difference is that instead of casting a ray through each pixel, we're going to cast a cone. Here, the radius of the cone is determined by the size of the pixel on the image plane, so the cone is modeling the whole volume of space that is visible by the pixel. This means that when we render this cone, we'll be averaging out all of the content within that visible volume, instead of just rendering whatever intersects with the infinitely narrow ray that was cast by NeRF. Now, instead of just sampling single points along each ray, we're going to slice up this cone into conical frustums. Here we're isolating one of those conical frustums by itself. Because conical frustums are difficult to manipulate analytically, we fit a multivariate Gaussian to the frustum, and this has a closed form solution. Then, instead of positionally encoding a single coordinate along the ray, we compute the expected positional encoding with respect to the Gaussian that we've constructed. Because of some nice properties of sinusoids and Gaussians, this also has a simple closed form that can be computed quickly. We're going to refer to these features as integrated positional encodings.
This is going to get a little...
Here's what the positional encoding used by NeRF looks like. We've got a single 1D coordinate x shown on the left there, and we're projecting it onto a set of sinusoids whose frequencies are all powers of 2 from each other. Now here's what our integrated positional encoding looks like, where we're modeling a Gaussian parameterized by a mean and a standard deviation. You can see that when the Gaussian gets wide, the encodings at higher frequencies get shrunk towards 0, and when the Gaussian gets narrow, those high frequencies reappear.
It's because you're not positional encoding a single point. You're doing now a Gaussian, and if you think about if the Gaussian gets bigger, then the higher frequency, they average out, and they just die. So they're just taking in, like if you think about it, everything in that Gaussian area is now a point, like everything in that area is something the point we're sampling. As we sample all these positional encodings, the expected value, guess what? If it's a large Gaussian, the high frequencies are just going to die, right? Because it's going to be centered around 0, right? And that's just like, ooh, how'd I get rid of this? That's, yeah. Oh, I went slides. Oops, I went too far. How'd I go back? Yeah, so
it's about 7% faster to the train than NeRF, and because we only learn a single multi-scale model, MIP NeRF has half as many parameters as NeRF.
Yeah, so it does better, and it actually allows for original NeRF was kind of very controlled environment, and this is what that actually allows for better generation of the real world stuff.
Now here are some results on this multi-scale Blender data set that we've been using, where NeRF is on the left and MIP NeRF is on the right.
Gaussian.
You can see that when the camera zooms out, NeRF tends to have a lot of jaggies and aliasing artifacts. And when the camera zooms in, NeRF tends to be oversmoothed and blurry.
Okay, yeah. Any questions? We good? Yeah, cool.
Cameras in positions, right?
It's just based off geometry, yeah, like the ray tracing, like how we normally do it. We just slice it up into regions based off the points we would already have sampled, right? Yeah.
Yeah, but we're sampling over like a space, not a whole like a single point, right?
Yeah.
So like, are we fixing the cone size? Like how large the area is?
I think it is fixed per pixel, yes. Because again, how each pixel would like geometry, they need it all captured. Yeah. So I think it's just like projection math stuff. Okay, cool. Yeah, so this is MIPNeRF. This is what they did. They did this kind of thing, sort of point. They do like they sample in this, and it's like better. They do the map stuff, and they do multi-scale. And then this is encoding. Again, it's a very definite encoding, but again, larger Gaussians wash out the higher frequencies. Yeah.
Like is the ground truth object blurred or like only the prediction?
I think it's the fact that if I'm farther away, it's more blurred, right? And that's the problem, is that if I have a picture here and then a picture here, it's like I don't know how to deal with these different resolutions and stuff, and I have to do aliasing problems and things. Yeah, well,
I'm still a bit confused, I guess. Is MIPNeRF, is it like a sampling method or is it also a training method? It's a training method.
And we're going to
it's like it's probably a training method, but it looks like do they also train using like the expected positional encodings?
I think they do.
let's look at the paper. Is integrated rather than casting array, we cast it for each queried point along array we consider is associated.
We train NeRF and MIPNeRF on a data set. So yeah, I think it's trained. Yeah.
I want the training objective is the same as the observed instead, right? Because I feel like the canonical sampling is more of like a sampling.
Maybe they just is it mainly just the positional that they affect? It might be because if they get rid of its positional information, it's like representing a Gaussian. I think that's the whole point, is that they're not sampling in that cone area. It might be that because you're this point, you're not just giving it a defined positional. If you wash out the higher frequencies, that's as if you're asking it for this general area instead. I think that's the I think that I didn't understand that. Yeah, I think that's really it. You're not sampling in this area, the Gaussian uniform. You're sampling the network. You're diluting the positional embedding, so it doesn't know where you are in here, and it's uncertain, right? So if you get rid of the higher frequencies, but you know that you're somewhere here, right? Somewhere in this area. Right?
Oh, so when you're training, you also have things like rays that are sampled in the context.
Yes. That's part of training. Yeah, as well. Another question?
It's kind of like regularization for the.
It's like regularization for the but it makes it's based off like geometry, and it makes sense in that it's motivated by that. Yeah.
Oh, fun fact. There's a paper in 2022 called Free NeRF by Grassley, who was in Boy's lab. And basically what he says, if you were to do few shot NeRF generation, a really easy way to actually make that work is just chop off the higher frequencies and don't.
Really?
Yeah, take the because what you're doing is you're making the position encodings less accurate, and by doing so, it has a bit more wiggle room freedom when it only has.
Yeah, it's regularization. Yeah. It's regularization. Yeah. Oh, next one. Wait, what is it? Yeah. I think I only want. Oh wait.
Yeah.
Okay. Okay. Next thing, pixel NeRF. So pixel NeRF, what it tries to do is it pretty much just does a convolution in front of the entire rendering process, and it actually lets it learn and remember like features of things. So this means that, let's say I see Jordan, and then I only have pictures from side to side. When I go to the back of his head in normal NeRF, it's just gonna be blah, right? But if I've seen a lot of like spheres before, right, I'd be like, his back of the head is probably also a sphere, right? I don't think I made slides for this, but look how well it looks. That's normal NeRF. So they gave it 3 images. That's normal NeRF.
That's great.
And you can see how like one angle looks really good, and then it goes really bad. right? Because again, it over-optimized for that single, but this is pre-trained on a bunch of different scenes. And it works very well. So you pre-train it on just understanding the world, and now if I have image here, that's enough for me. I don't need to get every single one. Because again, if you think about the original NeRF, it's kind of like doing the opposite of ML. It's not trying to generalize from the images. It's trying to overfit to the scene, right? The model literally like encodes and remembers a scene, right? So Pixel NeRF tries to get rid of that by literally just throwing like a convolution in front. Yeah, that's just one thing. So next thing, the guys, they came out again, same guys. This is probably like, again, this is the main NeRF methods. It's called MIP NeRF 360. So what's the 360? This is like MIP NeRF, the same authors, next iteration. They had 3 problems. Unbounded scenes. If you made really big scenes, it did very poorly. And then also large scenes, you need a larger MLP. That's hard and annoying. And then also the fact is you're gonna have these things called floaters, which are just Gaussians that just float, and they're very transparent, but they're very big, and they're kind of just annoying. They make the whole scene hazy, right? So that's a regularization technique. So they had 3 problems and 3 solutions. So we're going over the first one, which is unbounded scenes, right? You want very large scenes. How do you do that? These are our Gaussians. Again, it's a 2D example, very nice. Again, they had an 11-minute video I want to show, but I'll just go through fast slides here. These are your Gaussians that you're doing out in space. This is MIP NeRF, right? But we want to do 360. We want it to be unbounded. So but they can't. So the network has to work with the bounds. You're occurring from like 0 to 1 in the space, right? And we're asking the network, hey, what is this color at this position? But we can't go like 0 to a billion trillion. Like it doesn't go that far. It's very hard. So we need to somehow compress that space down to 0 and 1. And how they do that is they do this kind of like Kalman filtering warping stuff onto a unit sphere or like a radius 2 sphere. And this keeps it in a nice area. Yeah.
I love computer graphics.
Yeah, it's very cool. I love this diagram, though. It's very cool. Second thing they do, remember this thing, they used actually the original network in NeRF. This is kind of just like an inefficiency in NeRF, I feel like, where they densely sampled, and they used the color thing, and then they found that one, and then they sampled finer at that point. But they're like, wait, why are we using the color network to do the alpha? It gets producing RGB and alpha. That's a big network that does that. Can we just train a smaller one just to do the alpha, and then use the larger one that does RGB and alpha to distill that knowledge into the smaller model that just does the density estimation, not the color and density estimation. And this allows it to train way faster. It's pretty much an efficiency in NeRF, I think, pretty much. And then the last thing is the regularization. They have it so they enforce the regularization laws pretty much to make it so the density function, again, like you sample the networks, like this area is really dense. Again, this is the density thing, right? If you sample a network, it's like, oh, here it's dense, and then oh, here it's more, and there's probably an object here, right? Again, that would be like, here would be nothing, nothing, nothing. And then you have a high impulse at this door because it's transparent, and then like a very high one at the end, which is the ground, right? But what they're saying is that most things in the real world aren't this like large blocks that are somewhat transparent, translucent. Those are the floaters, right? We want to force it. So most things are impulses. Most things, you hit this point, it's 100% just that color, right? So that's a regularization they force on that, on the,
basically make edge sharper.
Yeah, they do that on the density estimation, right? So they pretty much just say the alpha, it has to be very, very non-transparent at a single point. That's what you want to generally tend to. Again, if you realize, oh, that's transparent, then okay. But most things in general, just don't try to have floaters, right? Most objects in the real world have high density at a single point, right? So those are the 3 techniques they did. 1, 2, 3, and that's MIP NeRF 360, MIP NeRF 360, and very good results. And they can do
Hi, I'm John Barron from Google Research.
John Barron again, bro. John Barron, this guy's crazy, dude. He like goes over it all.
With the ablation shown on the right.
So this is the parameterization, right?
Ablating the parameterization we use results in very blurry background.
So you can see if they don't do that warping in the space, it's very hard for far away things. So they need to warp it in that 0-1 space so the network can work with it better. That's the parameterization technique that we just talked about.
But you can see from the depth maps that distant areas don't have a lot. Ablating our distillation
This is the distillation
technique uniformly lowers quality everywhere. You can see a lot of flickering, and thin structures are quite a bit worse. Though this component's main purpose is to accelerate optimization, which it does by a factor of about 3.
Pretty good, pretty good. And last appellation, please.
Regularizer results in lots of these floater artifacts.
Yeah, do you see these? What we see, these little annoying things. This is what you want to get rid of. Don't have, the world does not have that. Okay, if you don't need to have that, don't have that.
Can't see that.
I see these things all the time.
These artifacts
But yeah,
can some
but you can see it looks like when it pause, it looks good, right? But then you realize, wait,
speed.
you see how like it looks like it's something from the background kind of like that looks like it's maybe like an opening in the trees. But then you like move and you're like,
Hard to
wait,
see in a
it's
still
like,
image
right?
and aren't penalized much by single image metrics,
Yes.
but they're very distracting when looking at a video and are especially visible when we look at depth.
Does that make sense, right? Because for single image metrics, you know, it doesn't look that bad. It looks like it could be real, right? But then, yeah, moving, you can really tell. So that's the 3 things we went over. We went over the first problem, which is the the Kalman filtering, right? The warping, geometry distillation to speed up, and then we do this for the floaters. And these are pretty good techniques. Yeah. MIPNERF 360, to be honest, MIPNERF is like, he's got that guy's crazy. Anyways, RegNeRF. So, I didn't put the date. I think this is 2022, I think. So this is RegNeRF. So this is RegNeRF. RegNeRF came out after PixelNeRF. Remember PixelNeRF, again, learning different things. And what it does is it's like, hey, I've seen this side of Jordan's face. I've seen this side. I want to look at the back. Oh, it's all bad. What happened, right? Because I didn't see it. Again, it's over-optimizing. It doesn't guarantee anything about the backside of Jordan's head there. But what this paper does, they literally just force, again, a regularization technique. They say, hey, the geometry should be smooth. That's how most things should work. And then also the colors, the patches of colors in an image, they should look like, that is a neural network, I'm pretty sure. So they say it should look like what a neural network would normally tend to see of images in the real world. That's how they do that. So they
also do like a
color.
VI, not a like a.
It's some weird model. I forgot what it is.
Like large vision model or something like that.
I think it's small. It's a very weird model.
I
don't know. Again, we can look this up. Again, the RegNeRF, they're very good.
300 citations, that's crazy.
Look at yeah. Paper real fast. Let's see. So they have the first loss method. Let's see. So geometry regularization, that's what we're talking about, where things should just be smooth. So if Jordan's head like this and this, the back should just be smooth, right? It shouldn't be just plain here. And then you look at the back, it's literally just like these 2 images splat together. It should be like, it should try to smooth out things if it can. And the second thing it does, wait, where is this? No radiance background geometry. Do they have color? Where's the color regularization? Oh, color regularization is right here. Yeah. So they do color regularization and they use, oh, they do here. Look, the normalizing flow model patches on the JFT 3 million. Yeah, 300 million. So whatever that is. Yeah, they use a flow model, I think, on patches.
Oh, okay.
So that does a color regularization, kind of appearance regularization, flow model, something there. And that just forces another type of regularization on the geometry. And what's very funny is that this actually does better than the PixelNeRF, which had a CNN, and you think it could learn features and things, but just forcing regularization is actually better. Yeah, it's simpler. It seems way simpler. It doesn't require pre-training. It doesn't require another part of the neural network. And it's generally better. Again, I think the other one can scale more maybe at some point. But the main thing is that if it's pre-trained on like objects and you give it a new kind of scene where it's like unbounded or something, PixelNeRF is gonna really mess up, right? Their RegNeRF technique works on like pretty much any scene and just always helps, right? Even here you have this kind of like blurriness that happens because again, it's a CNN trying to it over optimizes for the scene. It's too hard for the CNN to like generalize the objects in general. So a regularization technique is actually
have you tried just like combining these regularization techniques with PixelNeRF?
No, I haven't seen that. No. I'm not sure it would help too much though. Like I think you really need this in PixelNeRF. You really need like way larger, way larger. Yeah. I mean, also you can just give like Sora an image or something, and then now it's like it can do it all. So I mean, that's the whole point. Just do the CNN part. So next thing, this is the last thing. I think last thing. This is so. I didn't mention to you how long NeRF took to train this whole time. NeRF took like 3 days. Like a single scene would take 3 days. Because think about it, we're sampling a long array, we're ray tracing. That's for a single pixel of an image. Then we have to backprop the whole image, and we have many images. You can, yeah, it literally days. Like this used to take days. NVIDIA is cracked. Like they are crazy. They went, okay, we're just gonna optimize this and get 1,000 times speed up. They understand their hardware and like the stack so well, they can do this kind of stuff for so many things where like these hard guys are like, yeah, we're gonna speed it up by like insane amount of times, right? They literally just did like a smarter like ray tracing step stuff, and they got like a 10 to 100. They also use smaller networks, and they learned how to fuse them with like moving caches around and making so the model only loads once and fusing layers because they're NVIDIA. And then they also, instead of positional encodings, they did learned multi-hash encodings. And again, all of these together, 1,000 times speed up, which is like, again, like it's just crazy. Like this can now train in like, I think like minutes, like 10 minutes. Per days, like 3 days, which was never before 2022, which is like NVIDIA paper. This is crazy. It's called instant NGP, instant neural graphics primitives. And this can work with like anything now, with a lot of other stuff. Oh, that's Gaussian splatting. Okay, I'm just gonna go to the instant NGP again. I'm gonna explain instant NGP. Let's just go here. Yeah, so they can do a lot of cool stuff. Again, all these guys have presentation. It's so nice. I'm just gonna skip through it to the
Hello,
parts.
I'm Thomas.
Look at these guys. These guys are so. Let's see. Wait, there's a good part. I
The
think.
different direction.
Which means. Yeah, he says this. Is there anything relevant here?
Can give.
To be honest, yeah, this is some crazy stuff. They go here and they do like hashing and like it's very good. Anywho. Look at the results. That is trained. Did you guys see that? That literally just trained the time you looked at it. Let's wait for the gift.
It was trained in the browser?
No, not in the browser, but right. Oh, there trained. Let me. Sorry, it trained so fast you couldn't even. Oh, there it's done.
What?
Some of the these are smaller scenes, so they can train instantly. I think they're using better GPUs than like consumer, but they might use a cluster. They can train from instead of days to
minutes
or seconds for very smaller ones.
What
methodology that?
Oh, these 3 things. They did smarter sampling because they know how to ray trace things very well. So they do those optimizations. They fuse the networks together. So instead of doing multiple like dense networks, they can smash them together and push them all in cache at the same time. And then they also learn this kind of instead of doing the positional encoding, they do learned positional encoding. And those learned positional encodings are also multi-hashed resolution stuff. It's crazy.
Same methodology, but they just take advantage of their GPU.
Yeah, they know how to optimize it. It's from NVIDIA, so it's crazy though. Like altogether, this is 1,000 times speed up, which is pretty crazy. And again, like this trained, I think. Can I open video new tab? Let's see. Look at that, boom. Look. This is look that's real seconds. Whoa. Oh, it's getting better. It's getting better. I think it's pretty much almost done. Yeah. Compared to days, this was days before, guys. Days. Like 1,000 times speed up is insane. Not double, not whatever. This probably is on a cluster, I'd say, or something like yeah. But like look at this. So this is the right one is 34 photographs. That's 34.
34. Jesus Christ.
And it's pretty good. But the main thing is this is NeRF. 34 photographs. This is how good NeRF was, but the point is this is training very, very fast now. Yeah.
5 minutes.
So it's they only have like percentage for images?
Yeah. But they probably very strategically pick them.
Yeah.
Like video, you normally this is probably from they say video. Anywho, so back to slideshow. Okay, but we're finally here. We're finally here.
Gaussian splatting.
Oh, did I wait? Another video. Wait, did I not have an intro? I swear I had an intro for this. I don't. I'm just gonna I'm gonna explain it. I'm just gonna play another video because this is like a visual presentation, like, and having the graphics without video. Yeah, we're gonna watch this.
Gaussian splatting. What's that? It's a way to render stuff really high fidelity, really fast. It's a big deal because it's totally different from any existing graphics pipeline and is capable of rendering scenes that look like this at 144 FPS. The original research paper is 3D Gaussian splatting for real-time radiance field rendering. What does that mean? I'll explain how it works. Step 1, take a bunch of pictures of stuff from different angles, then use an old algorithm called structure from motion to estimate a point cloud from the pictures at different angles. Step 2, take every point in the point cloud and say you're a Gaussian now. I'm a what? A distribution that looks like this, but in 3D, and also can be skewed, which is what I like to call multivariate. Everyone calls it that. We also assign a color and an alpha. Now we can put all these Gaussians into one giant matrix with 16 columns and rows, one for every Gaussian. This is all the data we need to represent the scene. Sorry, no. Step 3, rasterization, meaning turn all these Gaussians into an image. How? The simplified version is, according to your camera perspective, project the Gaussians into 2D, then sort them by depth, then for every pixel, iterate over every Gaussian, front to back, calculate their contribution to that pixel, then blend them all together. Now we have an image. So are we done? No. Part 4, training. These Gaussians don't have the right values, so we need to train them, meaning adjust the values of the Gaussians so that they produce images that look like the original images. This is a lot like training a neural network, but with 0 layers, which is why it's so fast. The training also uses automated densification and pruning, meaning when a Gaussian is struggling to fit a detailed part of the scene, it splits into 2 Gaussians. And when a Gaussian's alpha gets too low, it gets removed. Now we have a trained set of millions of Gaussians that can be rasterized from any angle to produce an image. Okay, now what? Well, this is extremely new. It's kind of like when traditional rasterization was first invented, and then Doom came along and added shadows. And everyone was like, wow, you added shadows. And then came reflections, normal maps, indirect lighting, you know, the graphics pipeline. And this paper is basically reinventing step 1. Now you may be thinking, is the same as photogrammetry? No, because this is a rasterization technique, meaning it converts the underlying data directly into an image without the need for ray tracing, path tracing, or diffusion. So why didn't it exist till now? Because even though it's a simple operation, for it to look as good as it does, you need millions of Gaussians, which requires several gigs of VRAM. So is graphics about to totally change forever? Or is this an
That's that. Yeah, that's
Gaussian splatting?
Okay. Let's go to I have another that's the actual one. That's another video. Okay, I'll explain it. Yeah. So what they do is we have our camera positions. Yeah, go, Will.
Wait, but did also did you submit that video to Instagram?
No. This is sorry. This is their paper. This
Hi.
paper.
This is a short video presentation of 3D.
Yeah, so this is way more calm, and they're like, yeah.
Here we visualize the progress of the 3D Gaussian point cloud during optimization in a time lapse.
The main difference, I'll just skip ahead. The main difference between this, you're like, wait, nerfed it. So now you can actually look at these and you understand everything. You understand everything on here. Look, this is MIP nerf 360. You guys know that now. This is instant NGP. This is a really fast method. And if you look at the training time, right? Instant NGP does it in 7 minutes. This is MIP nerf. It takes 48 hours. There's no more nerf. Yeah. Right. Instant NGP 1,000 times speed up to 7 minutes. This is Gaussian splatting. They did 7K iterations and 30K. Our 30K should be done by now, probably. It's been more than 40 minutes. But you can see the time difference here, right? But if you actually look, this is the main difference. You're like, wait, instant NGP is not as fast as theirs. Why are we using splatting? It's because you're still ray tracing at render time, right? And that's the point. You're still doing ray tracing when you actually want to move around. So if you want to use this, it runs at like 9 FPS, right? Because it's ray tracing. But their method, it's just basic rasterization, like triangle meshes kind of stuff. And then the meshes aren't really meshes. They're these Gaussians that's in the space. And that allows you to actually run this at like 130 FPS. So we're going to be able to look in the viewer and run around there at 130 FPS. Compared to,
So the difference is that for instant NGP, they actually, every time they're rendering, they're querying a bunch of neural networks. Yeah. But for them, it's just like, oh, we have a Gaussian. Yeah. We sample.
They render it. They did literally just sort them by depth, render. That's it.
Okay, cool.
Yeah. And MIP performs a little bit better, but again, MIP takes so much time. And then compared to instant NGP, their 30K does a little bit better. But again, these are like a little skewed. These numbers, like, look, it's like 24 starts here. But yeah. Cool stuff. That's the main thing, is that they have the differential rasterizer. If we actually look here. So the initial, we can ignore this for now, but pretty much you have these cameras, you pretty much just put a bunch of Gaussians in space. They just exist. They're there. They're randomly initialized, right? What we do is we say, okay, I'm in this camera position in space. Render an image. Render all the Gaussians. These Gaussians are in space. They're just like 3D objects. Render them. And then you then say, okay, look at the original image. And then you say, let's say this pixel's black, but it's supposed to be white or something. Then you're like, okay, backprop that difference through. And then you can figure out with the differential rasterizer, they just figure out at this for this pixel, how much did each Gaussian contribute to it, right? And let's say the Gaussian was the wrong color, it would start to then increase to the right color. If it had low transparency, it would increase transparency. And then they have some other.
So fast, is it because it renders the whole image at one time? Or?
It doesn't have to sample a long array. It's pretty much just defining geometry in the scene and doing classical rendering techniques of just rasterization projection. Yeah, so it's like a classical technique instead of sampling a long array, something that's for one pixel, then doing that again, versus just sort all your objects, then look at this camera, do linear algebra to transform them and project them on the 2D image. Yeah. But then they also do two other things. They have it so, like that video said, if this Gaussian is getting stretched and it's like, hey, like I need you here to be green and here to be green. It's like, wait, I'm trying to do both. I'm trying to get there. It's just like I'll split into two. And then also, if it's a giant guy and it's trying to bend and trying to warp too much, and they have some like factor in math to do that, it splits into two. And they also have it so if I'm like decreasing this Gaussian to be like, I'm like, you should be more transparent, right? Because looking at both angles, like this area should be transparent. It kills it after some transparency value. And that's how it works. Again, they don't random. So this is the part I ignored. You can randomly initialize Gaussians in the space and they do an ablation. But what's actually more helpful is we did the structure of motion to get the camera position. We also have the point cloud. It'd be probably pretty smart to initialize the Gaussians at the point cloud. Because if they were uniform in space, you might have a bunch of floaters that just stay there. But if I initialize them at the actual objects, it's probably going to be better for training. And if we actually go look at their, what's the wrong one?
Can also be extracted.
If you go
Hi,
here.
this is the short video presentation. In this example, we scale down their.
Oh my gosh, what?
Can also be extracted.
How do I'll just go, can I go here?
Hi, Hypno 360, tungsten temples.
So yeah, here's
100
the
frames per this. Also did a careful ablation of points, sample.
Yeah, so here they did so this is random initialization, right?
For initialization, we initialize with a random set of points sampled uniformly in the scene.
Right. So you see all this blurriness and you have these images, because what they did is it's their whole scene, put a Gaussian here, Gaussian here, Gaussian here, Gaussian, Gaussian. They uniformly put it.
It's like a 3D grid of Gaussians.
It's 3D grid of Gaussians, and then they say render the image, do this backprop, manipulate these Gaussians through the differential rasterizer. But again, you're gonna have these little problems. So like, wait, we have the point cloud. Just initialize all the Gaussians to start near where the point clouds are, and that's probably gonna be better.
Yeah.
And yeah, it looks better.
The number of Gaussians, like in this object, it depends on how many points is in the point cloud.
It also is how much detail. Let's say there's a lot of let's say there's only 2 points, but then the image has a lot of detail. The Gaussians might have to split a bunch of times. There might have to be a lot of them to represent high frequency features. Yeah. So we're gonna see that though with our Gaussian we're gonna remade. That's gonna be so cool. I think. Okay. I'm gonna speed up a little. Yeah. These guys show it splitting and whatever. But yeah. Okay. Yeah. I think we're gonna let's look at it. Let's look at our Gaussian, guys.
Oh,
I think we're done. Look, yeah, I did when did it finish? 12:41. Yeah, it fit 40 minutes. That's how long it took.
Oh.
To do 30K. We're at 30K. So again, if we go back here, we did the 30K right here. Saves the 7K and 30K in the repo they have. So we're gonna go here. I want a full screen. I just want to make it bigger. Okay, we're gonna make it bigger here. I'm gonna use the Gaussian viewer. I'm gonna CD what the copilot CD viewer, CD bin, ls dir. That's what you do. That's not what I want. I want to copy this right here. Copy text, paste text. Okay, and then now we're gonna go to Gaussian splatting output / reading group. That's what we called it, right? Okay. Wait, this should.
before the starting code.
I think code's fine.
Oh.
Oh, snap. So now what we're gonna do, let's can I make this bigger?
Yeah, full screen.
I think I'll screen this and then
Yeah.
there we go. Wait, I can drag this in here, right?
Oh, yeah. Oh.
Okay, there we go. Okay, this is how many, wow, there's more people than was here originally. But so now what we're gonna do, we're gonna look at all the camera positions. So look, this is the video we took. And you can see every one of these frames looks photoreal, right? Because this is what it's optimizing for. But now I'm going to fly and move around. What? What? And look, it kind of messes up because it's never seen this angle before. So look, you can actually see the Gaussians kind of just sitting there. Right? Let's see.
Oh.
Oh, we're turning. Oh, we're going. Yeah, we can. So we can actually see.
Oh, I don't like this.
So look. So let's go and we can actually see, first of all, the initial points. So this is our point cloud, right? This is where all they were initialized from, right? And this is how it did destruction from motion. This is just using CoolMap and the basic techniques we explained before. And then we can actually do a cooler thing. We're gonna see this ellipsoids. Boom. So these are the Gaussians. These are the Gaussians that make up the scene right here. I think we can see.
It's real.
We can see. Does it say here somewhere?
Oh, 457,120. It's just loading. Yeah.
Where is wait?
Yeah.
Oh, right here. Yeah. That's not that bad. That's not bad. Yeah. I had a scene of UCSD was like 4 million.
Oh.
I wonder how much GPU actually this is taking. Oh, that's the thing. Hold on, wait.
It's lagging.
Task manager.
Yeah.
Let's see. Actually not that much. Yeah, barely. Yeah. For training though, you need up to 24 normally.
Okay.
But let's go back to the viewer. These are the Gaussians. This is I don't know why this is more laggy than the other thing, but like we can look at stuff. Look at the chairs, look at the whatever. You can see the floaters. You see the floaters, guys? Like in the air. These guys, they're very transparent. But
was just vaping.
dude, look at this guy.
Oh, man.
So we can also see, this is kind of cool. The splats, right? We can bring them down in size. So whoa, this is kind of cool, right? And we can see how each splat actually has a lot of properties. It has you can see it like some of the splats just go to a circle, but some of them have a very high variance along some axis. And how you represent these is, remember that 4x4 matrix guy showed? It's the covariance of itself. Like, yeah, it's defining the covariance matrix, which defines a Gaussian. They restrict it so it can actually represent a physical Gaussian in 3D. But yeah, look at these points. Whoa, you see like some of these like start to go brighter, right? Right. Whoa, you can see it slowly like, look, it's like, look at the ones on the right? See how they, each one of those Gaussians. I'm changing the size of the Gaussian. I'm like
scaling up.
Scaling the variant, yeah. And then again, we can go back to this view real fast if you want to look there. Whoa, cool. We did it, guys. Yeah. This is just cool. To look at. But again, if we snap to closest, these are actual frames. Look how good these look, right? And out of nowhere, we want to be like, okay, I want to move. Okay, sure. Move a little bit. You don't exist here. Right? And then we can keep going and we can do snap to closest. And we're like, okay, continue on the frames. And again, these are the frames it's optimizing for. That's why these literally look like the actual frames, photoreal. We're doing the opposite of Mel. We're like overfitting to the things. A question?
So this is I'm curious. Do you know what StreetView was? Like years and years ago, StreetView had a thing where you could look at the thing and you could look around a little bit beyond the position. It was before this stuff.
Around.
What it would have been.
Oh.
What? That's why you use Rustdesk.
Oh.
Source.
Oh, okay, whatever. We saw it. Okay, yeah.
I think Street View is.
Wait, sorry, Street View? How they move?
They used to have a thing. I remember a long time ago. I'd be able to pan around past the Street View car, and it would like kind of do that thing that you see in a NeRF where you go to the edges and it gets all.
Oh, then they might
It
have
was before NeRFs, I thought. It was like years and years and years ago.
they might have just done depth estimation stuff and then projection things.
I think one of the parts of LiDAR.
They do have LiDAR, and that's how they're getting the 3D information. But if you're moving from where the snapshot is, I would assume they just use depth information and they kind of do some warping with that. Yeah. Okay, we have like 10 minutes left. I'm just gonna do I have I don't have size base, but we're just gonna go to things because they're good. So let's just look this up. What's this thing? Dynamic 3D Gaussians. What's this? So Gaussians came out like summer. Yeah, summer. Yeah, like a week or two, like 2-3 weeks before school started this year. And there hasn't been too many papers, but some of interesting notable ones is dynamic 3D Gaussians tracking persistent. Again, these pages are really nice. If you want to look at Gaussians or NeRFs, like it's like like think about what papers have these many visuals and like you know what I mean. It's very, very nice, and they always have a video explaining. But what this does is it tries to track Gaussians movement. So they have all these cameras around. Technically you need that other dimension. So you need all the cameras to be in those spatial locations already, and then you take snapshots every time frame. But what they have is they have the Gaussian sitting in space, and they try to do estimation of should this Gaussian be standing still? Should I have to create a new Gaussian, or can I move Gaussians around? Right, and that's actually they're tracking. Each one of those I'm pretty sure is corresponding to a different Gaussian that they're tracking through space, right? And again, the ball can be just one Gaussian. You need to create a new one for every single one. So it's again like kind of like a video 3D representation compression. And this came out really fast after the other one. I'm pretty sure it might be the same guys who worked on it or something. I don't know. It was very fast. I remember it was like one of the instant things there. It was like super cool. They do rotational tracking as well. Ground truth stuff. Yeah, in the line. Oh, I don't know what this is. Those are the Gaussians. Those are when they remember how we scaled them down. Yeah. So you can see those are the Gaussians. And you can see it's the same one. It's not like creating new ones out of nowhere. Oh, what is this? It's from like I think one of the data sets. Yeah. Same with this one over here. Anywho, that's one. To be honest, I'm just like going through these, whatever. I think this is the other one I saw. This one's cool. Again, 4D, people love 4D. What is this one? My computer's lagging. I think this is another technique that tries to do it.
Hello. With only focus on statics in the origin.
Yeah, there's some other ones. And look, it's like while they're moving, which is kind of cool. I think this is another work. I think the other work is like the more cited one. I don't know.
The other work requires like that setup of like what cameras.
Yeah. Oh, yeah. I think that's the difference. Yeah. This one's actually, yeah. And then Gaussian Dreamer is another cool one.
Yeah. I was gonna say it's
not Gaussian, but it's.
Hello, reviewers. This is Gaussian Dreamer, fast generation from text to 3D Gaussian.
Yeah, Gaussians are a thing. It's cool. 3D Gaussian splatting is really cool. Works fast. You can actually run in real time.
It's just the same as the diffusion one, where it's like you're using a diffusion model to like backpropagate all the way back to the Gaussians.
Yes.
Okay.
Yeah. The main method though is this differentiable rasterizer that didn't exist before. If you actually go look at the paper, that's the main component. You need to somehow differentiate from Gaussians to the image, and that's hard. Again, they use like sorting, and then they have like a buffer that then corresponds to like at that pixel location, the buffer stores all the Gaussians that contributed to it. So then you can backprop through to each of the Gaussians, and then you have to do color transparency, and then also last thing, with NeRF, we had an angle, we were looking at it. How Gaussians work is they store another component, which is actually spherical harmonics. So they actually can store specular information of you're looking at from this angle or this angle, the Gaussian looks different. Did they cover that? You can click the paper real fast. Wow, this is taking forever. What if I make it by, yeah, still like what? This shouldn't be. Come on, come on. The other one was like 150. They had a lot of images in the other one. There we go. This is the original paper. They had the things. Wait, what was I looking for? Control.
Specular highlights thing.
Spherical. Yeah. Do they have a section about it? Maybe they don't.
They just say
Yeah.
a lot.
The direction, appearance, whatever. Spherical. Look here. Yeah, I'll just look up. Whatever. Harmonics. Yeah, this is what they look like. So they store these in the Gaussian. They say how much should this be? How much should this be? So you can look at a Gaussian from a different angle and it looks different. Again, like if there's a glare in that iPad, I can, it's not projected onto the iPad and it's not just the color like 3D scanning. It's actually, I know it's a different angle, which is cool, cool stuff. So it's as good as NeRF, or better if you want to think about render time. And yeah, that's about it. That's about it. Thank you for coming. Any other questions? No, we're good. Or yeah. Oh well. How's it going?
Just to clarify, so like neither like lyrics nor Gaussian splats actually model like light sources, right?
Model what?
Like they don't model light sources, or like basically they model all objects is probably like object color. But I guess like unlike ray tracing, you don't have like light sources and then like helping them out, right?
No, I don't think so. What's cool is that
because instead of just modeling like the color and then like the albedo, which is how much it like the transparency, it becomes okay. You have to somehow model the material.
Years ago, before the
thing, it's like how do you even start doing that? I think there's some NeRF works out there that's trying to model that directly. So computer graphics people aren't as mad at you when you're like, oh, use this. You're like, this is a 3D mesh. I don't give a crap, right? Like, because instead of just generating like the transparency and the actual color itself, you're also generating like what's the material properties of this thing? How does it reflect light? How does it like refract light? Like stuff like that.
So a funny thing though, how is it learning? Like, let's look at this real fast. How's it learning the reflections? That's pretty crazy, isn't that? Like, how's it doing that? Right? And you're like, maybe it's specular, but no, it's like actually look, it's like reflections. That's insane. This is NeRF, I think. This is splatting, yeah. How's it doing that? It does an old video game technique for reflections. It actually, you look, it creates a copy of it underneath the table.
That's crazy.
So that's what it does in mirrors and stuff. If you look at a mirror, it's actually just going to create a duplicate of your room or something in the mirror. So it creates a copy of it underneath. And that's a little trick for you. Again, it doesn't have to learn an actual thing. It just has to look good from all the angles you gave it.
It learned this.
It learned because the best way for it to do that, it realized, wait, that looks like, think about when you look in a mirror. If you're just trying to create a 3D world and you don't know mirrors exist, you're like, oh, there's just for some reason a weird copy of this room in the other place there. That's weird. And that's what it does here. And it just learns that. I
guess originally, this should actually come from the original SFM, right? Like when the original SFM is extracting that feature, like to the SFM, it's like, oh, this feature is moving as a moving camera.
Yeah.
It's like it must be something under it.
Reflections mess with structural motion, I think.
Yeah, I think that's maybe what's happening.
Feature tracking is hard, yeah.
It's like the point on initially already had under it, and then Gaussian splatting is like, oh wait, and that's good actually.
Yeah. We did the zoom in? Yeah. Wait,
no, it's not.
Okay, I'm gonna stop share.
Okay, cool.
Okay.